All right, so let's get started. All right, it is my great pleasure to introduce Laura Tomkins. She was born in the UK and grew up in Chapel Hill. She actually started working for me as an undergrad in 2015. And then graduated from NC State with a bachelor's in meteorology and a math minor in 2017. And then she went off to University of Kansas to work with David Meacham on marine clouds. She completed her master's degree and had some conversations as she was finishing up and what she wanted to do next. I was able to convince her to come back. And I think part of the reason was the excellent program in the Center for Geospatial Analytics provides a kind of wider foundation than just a meteorology degree. And that was intriguing to Laura. And also, I've got to say, really appreciated all the support from the center and just the very student-centric, proactive help all along the way. So she's been here, she started in fall 2019. Then obviously we had COVID. And she's been remarkably productive. Just to give you some highlights, so far, she has 7 papers in the referee journals. There's at least 2 more coming that are in preparation, one first authored and one co-authored. She has several data sets out in public repositories, and she also has 2 different radar processing algorithms in public repositories. She's won 2 outstanding student presentations for 2 different presentations, one on her master's work and one on her Ph.D. work. She has 31 conference abstracts. She's been in the field for a number of field projects, most notably as related to this presentation, the NASA Impacts Field Project, where she served as both an aircraft scientist and a forecaster. And I think also I just want to note within the group, she's been a fantastic mentor.
Yes, signal lost.
To the undergrads in the group and really helped train them and bring them along, and they've contributed. And she's also a great team player, and I think that's a testament to just her contributing to other people's work. As I said, sometimes as a co-author, sometimes an acknowledgement, but just yeah, she's been remarkably and productive. So I'm going to turn it over to her.
All right, thank you.
One more thing. Sorry. One more thing. So she likes to cook, bake, and spend time in the backyard with her cat. And she has a job. She's going to be starting in April as a senior atmospheric scientist at Karen Clark and Company, which is a catastrophe modeling company. Okay, now.
Thank you. All right, okay, I'm just gonna get rid of the meeting controls. I hope that kind of stops things popping up. Okay. All right, well, thank you everyone for being here. I really appreciate having a lot of people in the room and a lot of people on Zoom. So today I'm gonna be talking about my dissertation work that has focused on kind of synthesizing a lot of different characteristics about winter storms. And I've been looking at over 10 years of data. So yeah, I'm excited to present what I've been working on. I would also like to just quickly thank my committee, Sandra, of course, Dr. Parker, Dr. Tolbier on Zoom, and then Dr. Perry. Okay. So just to start out here, I want to talk a little bit about winter storms in general, kind of what are they? So here I have a satellite image from a winter storm. This one, you can kind of just see a really large scale structure and how kind of expansive these types of systems are. This one in particular even produced some snow in eastern North Carolina. And so kind of looking at this from a more idealized perspective, here I have some graphics which show the progression of a low pressure system. So you might recognize this from your local broadcast station, where we have a low pressure system and it kind of moves and develops The green area kind of represents where we might expect precipitation based on these fronts and things like that. I don't know. I'm not sure like if that's gonna just, okay, I guess it's just gonna keep popping up, but just bear with me here. So yeah, so then the next thing I want to talk about is sort of how this all relates and in general why we care about winter storms. So here I have a forecast graphic on the left-hand side. The top is the 24-hour forecast prior to the event, and the bottom is the observed snowfall of what actually happened. So this is from an event a couple weeks ago, earlier in February. You can see that prior to the event, the Boston area was forecasted to receive between 8 to 12 inches of snow. Lots of preparations were in place, schools got canceled, but ultimately what happened is less than an inch of snow actually fell. And so this sort of really highlights how our forecasts still quite aren't there. We still have a long way to go. And just in general, like it's really important to understand these winter storms, to understand kind of the impacts and make sure that we have accurate forecasts. So now I kind of want to step into the radar observation. So here I have an image of a winter storm in 2006. This is a radar image from several radars in the Northeast US. In general, this is kind of not showing the full scope of the storm because we don't have radar coverage over the ocean. And this is kind of representing a little bit more about the precipitation patterns. And so one thing here is that in these winter storms, we often have what are called snow bands. And so you can kind of notice that there's a lot of linear features in this radar image. And so the snow bands are these elongated features of locally enhanced reflectivity. So in particular, we have these larger, more continuous features, which are known as primary bands. And these have been associated with frontogenesis, which is kind of a measure of the large scale upward motion and just in general where we see favorable precipitation development. On the other hand, we have these smaller features which are known as multi-bands, and these are a little more unclear in terms of what the forcing mechanism is. There's a lot of research that's ongoing to kind of understand the processes of multi-bands, but ultimately kind of what's been driving this research is understanding how these features impact what's actually going on at the surface. Like, do they enhance kind of the snowfall? And so one of the complications, here is that when we're looking at radar observations of snow, it doesn't always mean more mass. So when we're looking at radar reflectivity, we often associate the stronger areas of reflectivity with more intense precipitation. But in the case of snow, we can have processes such as riming, which I have shown in the blue image, where we have super cooled liquid water, which freezes onto the ice crystals. And this both increases the mass per unit volume and it increases the radar reflectivity. However, we can also have situations such as aggregation, which I've shown in the green box, which is when the ice crystals sort of jumble together. So this actually doesn't change the mass per unit volume, but it does increase the radar reflectivity. So it's just, again, kind of adding this complexity to our interpretations of radar observations of snow. So now I'm going to present sort of my main research goal for this project. So my main research goal is to understand the relationship between these several characteristics and the surface snow rates. So the first characteristic I'm going to talk about is storm structures. So here what I'm getting at is when and where in the storm does heavy snow occur. The next part is the locally enhanced reflectivity features. And with this, I'm trying to get at are snow bands associated with heavy snow rates. And then finally, we also see these Doppler radar observed velocity waves. And I'll talk a little bit about that later. But here we're trying to understand if these velocity waves play a role in enhancing surface snow rates. So first, I'm going to present a few methods that are kind of general to the project as a whole. And then for each category, I'm going to present individual methods and background relevant to each. So to start off, a lot of the work on winter storms and snowband processes has been done with case studies. So looking at individual cases that produce really strong snow at the surface and are very impactful. What I did was I actually wanted to look at a really broad, large case or really large sample to kind of understand processes over the kind of whole spectrum of events. So in the map on the left-hand side, I have ASOS stations. So these are surface stations that report things like temperature, pressure, precipitation. These stations in particular, they produce daily summaries, and they produce daily summaries which include the snow depth. So in order to be considered in the analysis, I'm choosing days where at least 2 out of the 14 stations produce at least 1 inch of snow at the surface. And so this sort of just informs on the general cases that I want to look at further in detail. This leaves me with 264 days between 2012 and 2023. So then once I have my cases, I kind of look in a little deeper and I'm looking at the hourly ASOS surface station data. So here I have more stations. I have stations kind of all over the Northeast. And again, these are surface stations. They're usually at airports. And they're reporting, in this case, they're reporting hourly observations of temperature, pressure, precipitation. In particular, I'm looking at the precipitation rate at all these stations. So I have an example on the right-hand side from the Boston station for an event in February 2021, where each observation represents the precipitation that accumulated over that hour. And I want to point out here that before, when I was determining the events that I wanted to use, I was using the actual snow depth. But because snow depth depends on a lot of different factors, here I'm actually using the liquid equivalent. So this is sort of the mass of the precipitation once it melts down. And this sort of helps to kind of eliminate some of those extra uncertainties and get a consistent measure from storm to storm. I also want to note that I'm using only kind of the most reliable observation. So I wanted to make sure that the station had reported snow for at least 4 hours to be considered in the analysis. And then I'm also excluding any observations where the wind speed is too high, just to exclude blizzard conditions. And then I'm also just using the stations where we have the most reliable observations for frozen precipitation. So when we consider that one sample is 1 hour at one ASOS station, we are left with over 17,000 samples over all of the stations and over all of the days. I also want to point out that I'll be talking a lot about heavy snow. And when I say heavy snow, I'm defining this as greater than or equal to 2.5 millimeters per hour. And this has been cited in the literature. So the next kind of data set that I want to talk about that's sort of common to all of these different things is the data set from the NASA Impacts Field Campaign. So this was a project that was aimed at kind of collecting observations in winter storms, in Northeast winter storms, to kind of understand some of the processes going on. And so in particular, this project, it had 2 aircraft. One was the P3 aircraft, which actually flew inside the storm and took observations, in situ observations of the microphysical processes. And then we had an ER2 aircraft, which flew at 20 kilometers and had several different remote sensing instruments on it, including passive microwave radiometers, but it also included several radars with 4 different frequencies, which is sort of the main data set that I'll be using. And so this project ran in 2020, 2022, and 2023. And so we got a few kind of samples of data which have been really valuable that I'll be talking about. So before I kind of dive in and get started, I want to really talk about where this is going and kind of what we found to kind of set up the kind of broad motivation for the project. So because I was looking at over 10 years of winter storms, these are kind of the main points that I found. What we found is that heavy snow rates are actually pretty rare in these storms. 75% of the hours had light snow rates, less than 1 millimeter per hour. Only 6% had heavy snow rates. We're also kind of finding that the snow bands or the enhanced reflectivity features are actually kind of a distraction since they're rarely associated with heavy snow rates. What we are finding though is that locations that had long durations of snow were more informative when it comes to forecasting high snowfall accumulation. Okay. So to start out, I'm going to be talking about the relationship between the storm structure and evolution and surface snow rates. So this is, again, getting at the when and the where in the storm are the heavy snow rates occurring. So again, I'm just bringing back this image here to talk about how the extratropical cyclone develops and kind of putting this into context of where we get heavy snow. I also want to talk about how between each of these images, as the low pressure develops, the pressure is usually changing. So it's either decreasing, indicating that the storm is strengthening, or increasing, indicating that the storm is weakening. So one of the things that we do is we can actually track the location of this low pressure center. So this is an example that I have from December 2020, where the top is showing a map of the low pressure center location, which is colored by the magnitude of the pressure. And then the bottom is a time series of that pressure track. And so here we can kind of see a pressure that's sort of developing over the Carolinas, which then moves offshore and moves up the coast and continues developing. I'll also talk a little bit about the term pressure tendency, which is the change of the pressure over time. So it's essentially the slope of the line in the bottom panel. So how much is the pressure changing per hour? When we look at all of the low pressure tracks for the entire data set, the left-hand side is just plotting all of the tracks on one map. It's kind of busy, but it just highlights how many tracks that we do have. And on the right-hand side, we have the density of the low pressure tracks. So the darker the color indicates the more low pressure center locations for that given box. And so what we see here is that there's really a tendency for these low pressure centers to be off the coast of or offshore. This is partially because of how we defined our winter storm. We're looking at those events that are impacting the Northeast US, but it's also just a favorable location for low pressure development. So the first thing I'm going to show is the distribution of precipitation rates relative to the low pressure center. So on the left-hand side, I have a plot where the low pressure is in the center of the plot, and each point is the precipitation rate at a station just relative to the low pressure. And so it's colored by the darker colors indicate a higher precipitation rate. And what we kind of see here is there's a general pattern for a lot of observations in the northwest quadrant. So when I talk about the northwest quadrant, I'm talking about it relative to the low pressure center. So I kind of have that highlighted in this box here. Generally just we see a lot of observations in the northwest and northeast quadrant. And I think this is partially just due to the general favorability of precipitation development in winter storms. So here I have an idealized schematic. The top one is from earlier in the storm and the bottom one's from later in the storm. The red area represents where we're seeing frontogenesis or large scale motion. And it's also where we see the higher precipitation rates in our data set relative to the low pressure center. Similarly, this is a graphic which is showing where it's showing the microphysical properties of snow relative to the low pressure center. And so the locations I've highlighted in purple indicate where we're seeing heavy riming or where we're seeing those super cold liquid water freezing onto ice crystals. So in general, this is where we would expect to have a higher precipitation rate because we have a higher mass of ice crystals. So in general, this is sort of consistent with what we see in the literature. The next thing I'm going to show is I actually subset this figure by how the low pressure center was evolving. So on the left-hand side, we have a situation where the low pressure center is either slowly developing or actually weakening. And on the right-hand side, we have situations where the low pressure center is rapidly developing. And so the rapidly developing case, you can see that there seems to be a preferential location for snow rates in the northwest and northeast quadrants. And we also see that in particular, there tends to be higher snow rates closer to the low. On the other hand, we have for the slowly developing or weakening case, there's not as consistent of a pattern. It's a little more sporadic and spread out. So the next thing I wanted to look at is the distribution of precipitation rates relative to the station pressure tendency. So here we're trying to understand when in the storm does the heavy snow occur. So on this plot here, this is a 2D distribution where the x-axis represents the 3-hour pressure tendency and the y-axis represents the precipitation rate. Each bin is colored by the number of hours for those given combinations. I've also annotated where purple is weakening storms and red is strengthening storms, and I've also indicated where we're seeing that heavy snow. And so the first thing that kind of stands out is that most of our observations are actually light to moderate. So we're seeing a lot of points clustered in the bottom part of this graph. And then the second part is that when we do see heavy snow, almost all of those, 86% of the observations are observed when the surface pressure is decreasing, which indicates that the storm is strengthening. So to summarize this first section here, I have, again, repeated the plot here. And so what we're seeing is that higher snow rates are likely to occur closer to the low pressure center in the northwest and northeast quadrant, which is consistent with what we see from previous work. And then we're also seeing that heavy snow rates are more often occurring when the station pressure is decreasing, which indicates the storm is strengthening. Okay. So now I'm going to move on to the next section, which is exploring the relationship between locally enhanced reflectivity features, i.e. those snow bands, and the surface snow rates. So for this part, I want to kind of go through a little bit of background about radar and just in general, the structures within winter storms. So this first figure I have here is from a radar on a research radar on Long Island, and in this case the radar is scanning up and over, so it's doing vertical cross sections. The x-axis represents the distance from the radar, and the y-axis represents the height above the radar. In this case, south is on the left-hand side and north is on the right-hand side. So the top field that I have is what's known as spectral width. And this here is a measure of turbulence. So the darker the color, the higher the spectral width and the more turbulence we have. And so I've annotated in this green box where we're seeing at the top of the echo kind of a lot of turbulent motions, which are actually indicative of overturning circulations, which in general is sort of where we would expect precipitation to develop. In the middle panel, I have the Doppler radial velocity, which is measuring the velocity component along the beam of the particles. So it can only really measure if the particles are moving towards or away from the radar. In conjunction with this, I have a wind profile on the left-hand side, which is from a similar time. So here, this is showing how the winds change with height. And I also put a little figure on the far left-hand side, which kind of just shows what these wind barbs kind of mean. So it's essentially indicating where the wind is coming from. So in the Doppler radial velocity, we can see that at the top of the echo, negative indicates that the precipitation is moving towards the radar, and red indicates that it's moving away. So at the top of the echo, we have winds that are moving from south to north, which is consistent with what we see in the wind profile. In the center, we have an area where the winds are close to zero, which could mean light winds, but in this case, it actually also could mean that the winds are moving perpendicular to the radar, which we see also in the wind profile. Then there's another layer below where the winds are moving from south to north, and then finally near the surface, the winds are moving from north to south, a complete shift in the wind. And then finally, at the bottom, we have the radar reflectivity, which is a measure of backscattered energy, kind of indicates the intensity of the precipitation. So I have annotated here these kind of features where from the overturning circulations in the spectral width, we get precipitation growth, but then as the kind of precipitation falls to the surface, it gets transported by the wind. So the next thing I'm going to show is an animation of this, just to kind of highlight how a lot of these features evolve and how a lot of the features kind of are related to each other. So again, in the spectral width, there's kind of a lot of turbulence and a lot of overturning circulations at cloud top, which kind of ends up producing precipitation, which you can see in the radar reflectivity. And then once the kind of precipitation forms, it gets transported by the velocity. And so with this, I kind of just really wanted to highlight how, first of all, how the high spatial resolution of these observations and how there's really a lot going on here. The x-axis only covers about 60 kilometers, so you can really see like how detailed and how fine scale a lot of these structures are. And it also highlights how what's really forming aloft does not end up falling straight to the surface. It kind of ends up just getting blown around, in some cases, not just left and right, but in and out of the page as well. So the next example I want to highlight is some data from our NASA Impacts project. So here I kind of have these observations co-located. So on the left-hand side, I have a reflectivity map that's stitched together from several radars. And on the right-hand side, I have the radar data that is from along a cross-section. I'll play an animation and you'll see the aircraft moving, and then you'll also see a vertical line in the radars, which indicates where the aircraft is. Because there's 4 different frequencies, I have those all plotted. So the top one is the lowest frequency and the bottom is the highest frequency. So it's more sensitive to clouds, but also it can be more attenuated. So as I play this, you'll see how the aircraft kind of moves over some kind of elongated reflectivity features, likely snow bands. And then you can see kind of what those look like in the vertical and kind of how we were sort of expecting to see very kind of like vertical features, but ultimately the features end up getting tilted and smeared out as they fall to the surface. And so I kind of have annotated here the kind of bending features the bending features of the enhanced reflectivity. So this just again sort of indicates how what we're seeing in the kind of overall horizontal reflectivity images, there's a lot more detailed story going on in terms of what's happening in the vertical. So I again have a couple more examples from the NASA Impacts project, which kind of highlight this message. So here I actually have the wind profile that's plotted along each of the legs. It's difficult to see the barbs, but I have them summarized in the plots on the left-hand side. So these plots are CFADs, contoured frequency by altitude diagrams, which are highlighting the change in wind speed and direction with height. So on the far left, we have the wind speed, where the x-axis represents the speed and the y-axis represents the height. So you can see at the top of the echo that both of the wind speeds are near 30 meters per second, which then decrease towards the surface and then increase slightly again after or below 2 kilometers. The middle plots are wind direction. So this is indicating where the wind is coming from. So I also have annotated in the black arrows, these are the directions of the flight tracks themselves. So in the wind direction, you can see for both of them, in the first case, the aircraft is actually flying from the north, and in the bottom case, the aircraft is flying from the east. And so in both cases, at the top of the echo, the wind is pointing perpendicular to the direction the aircraft is flying. So this indicates that as soon as the precipitation forms at the top of the echo, it's immediately being transported away from the flight track as it falls to the surface. And again, we can kind of see like how the wind direction changes with height. And so when we look at the reflectivity patterns from the flight tracks, we can see how the wind speed and direction can transport the ice particles sometimes more than 50 kilometers in the horizontal, which really kind of complicates the interpretation of reflectivity. You can see in the top example, you have a lot of bendy structures and a lot of kind of smeared out things. The bottom panel is a little more kind of consistent, but likely still kind of having a lot of transport of the precipitation particles. So now I kind of want to connect this all back to the horizontal scanning radar observations. So this is an example of a kind of cartoon of how a radar at the surface scans. And so the x-axis represents the distance from the radar, and the y-axis represents the altitude above the radar. And then the green line represents the beam of the radar. And so the further away from the radar, the beam gets wider and higher above the surface. And so if you think when you have kind of a precipitation area, like I've annotated in this gray area, you can see that based on where the beam is relative to the radar, it's scanning a whole different part of the storm. And we're also, because we're seeing so much fine scale detail, it kind of, again, really complicates kind of what we're seeing at the surface. And again, I just have the bottom of the two definitions of reflectivity and Doppler velocity. So this is sort of the main data set that I'm using for this particular part of the study. So this is radar data that's combined from several individual radars in the Northeast US. The far left is the radar reflectivity, which we've talked about quite a bit. You can see here that there's some snow banded features. One of the issues was, though, is that based on who you asked, you might get a different, they might identify different snow bands. And so we really wanted to create this objective feature detection for the snow bands, which is on the far right panel. And so here you can kind of see that there's a strong snow band that's kind of over the New Jersey, Connecticut area. And then we also were able to identify both strong and faint features. And so we can see some faint snow bands that are in over Pennsylvania and New York. And then finally, the teal color represents the background echo. And so again, this sort of just highlights kind of, I'll just bring back the motivation question of we're trying to understand if these snow bands or these enhanced reflectivity features have an impact on the surface snow rates. So one of the challenges is that the NEXRAD or the radar observations occur every 5 to 10 minutes. And we only have, or we're using hourly ASOS observations. So we needed to kind of come up with a way to relate the kind of 5 to 10 minute NEXRAD observations with the hourly ASOS precipitation rates. So here I have an example from Boston where you can see that there are several kind of snowband features on the left-hand side in the feature detection. And then the right-hand side is just looping through the time series of the precipitation rates. And then the other lines represent the area within the circle. So the circle is 25 kilometers, and we wanted to choose this instead of just looking directly above the ASOS station because there is a lot of variability. And so we chose 25 kilometers. And then in order to relate them hour to hour, we calculated this integrated statistic, which is called, or which I call the area times time fraction. And so I have some examples here of how we could get a fraction of 0.5. For example, if you had 100% coverage of those kind of yellow features within for 30 minutes, that would give you a fraction of 0.5. If the features were only covering that that circle for an hour, half of the circle for an hour, or if you had 75% coverage for 40 minutes. Those would kind of be just a few of the many ways that you could get a fraction of 0.5. So now I'll kind of dive into my results and kind of what this is showing. So on the left-hand side, these are two plots. They're summarizing the same information. So the left-hand side is a 2D density plot, and the right-hand side is a bar chart, which is summarizing the information in the density plot. So on the x-axis, we have that feature area times time fraction. And on the y-axis, we have the liquid equivalent precipitation rate. And then again, each bin is colored by the number of observations for that given category. And so what we're kind of seeing here is that most of the time, the locally enhanced reflectivity is associated with low snow rates. We were sort of expecting to see, okay, like if we have a lot of feature area covering the station, we might expect to see a higher snow rate, maybe something kind of like along this line right here. But ultimately, that's not really what we're seeing. We're not really seeing a really strong and clear relationship between these two measures. And so the next thing I want to do is just go through an example of each of these different types of scenarios to kind of see what these situations look like. So for each example, I have highlighted on the density plot where these observations fall, and then I have them annotated in the time series in the red box. And then on top is the feature detection field. So I'll go ahead and play this just so we can see what this looks like. This is an example from Albany where we see very strong features covering the station. And we also see pretty high precipitation rates. This part in the middle, these observations were not used because they had a high wind speed. But we can kind of see here how this station was there was a band, an enhanced reflectivity feature over this station for a good persistent amount of time. And we also saw heavy snow rates. However, this really only accounts for about 1.5% of our samples. So it really doesn't happen very often at all. The next scenario is where we do have a lot of features, but our snow rates are still fairly low. So this is an example from Rhode Island here, where we have features surrounding the ASOS station, but ultimately low snow rates. And this accounts for about 4.6% of our samples. And then this scenario is where we have most of our samples. This is where we have not much in terms of locally enhanced reflectivity surrounding the station, and we also have a low snow rate. And this accounts for almost 90% of our samples. And then finally, we have this scenario where we have very little in terms of feature area, but we have high snow rates. And so this accounts for about 4.8% of our samples. So just for the sake of time, I'm going to skip these slides, but essentially I performed some sensitivity tests to just understand how sensitive my results were to different things. And ultimately I found that they weren't sensitive, but I can go over this at the end if anyone is curious. The next thing I want to show is what the distribution looks like when we don't have any locally enhanced features over the ASOS station. So in this case, this is where we only have background echo, or we only have that teal color surrounding the ASOS station. And so again, the 2D distribution is showing the background area times time fraction on the y-axis, where 1 would represent full coverage of that background echo for the entire hour, and 0 would represent no background echo for the entire hour. And so what we're again seeing here is that the snow rates are typically very low and rarely exceed 2.5, that heavy threshold 2.5 millimeters per hour. The next thing I wanted to show is what the distribution looks like when we just consider all types of echo. So this is both considering features and background, any type of echo surrounding the station. And so again, that's shown on the x-axis, and the y-axis, the precipitation rate. And so in this case, almost all of the heavy snow observations occur when the echo area of times time fraction is greater than 0.5. So this actually implies that in terms of heavy snow forecasting, whereas before with the features, it was kind of a mixed in terms of what we saw. In this case, almost all of the heavy snow is occurring when the echo area times time fraction is above a certain threshold, which indicates that the duration of echo is more important in terms of forecasting heavy snow than the locally enhanced reflectivity features. Okay. So just in summary, we didn't find a clear and consistent association with high hourly snowfall rates. Most of the time, the snowfall rates are low. We think this is likely because there's little in terms of vertical column continuity in the vertical in terms of reflectivity enhancements. In general, our interpretation of radar reflectivity in snow is very complicated. Enhanced reflectivity doesn't always mean enhanced ice mass, and snow doesn't fall straight down. It can be transported by the wind, and it ends up being tilted and smeared on its way to the surface. Okay, so my final category or my final characteristic is talking about the relationship between velocity waves and surface snow rates. So I'm just going to talk briefly about what I mean by a velocity wave. So this is an example here where on the left-hand side, we have two sequential Doppler or radial velocity images. And so we sort of noticed that there was a lot of kind of wavy or striated features in the field. And so essentially when we subtract two sequential fields, we can get a radial velocity difference and then extract or calculate it into a binary field, which we can then stitch together, and we kind of see these wavy features. As I mentioned, or not as I mentioned, but compared to the enhanced reflectivity features, these waves are a lot more challenging to automatically detect. So we had to take a slightly different route in terms of determining the location and time we had waves. So I guess I should really mention too, because we saw these features, we were kind of just curious to understand if they had any impact on the surface snow rates. So in order to classify the wave presence, we focused on these two smaller subregions within our general Northeast location. And so for each hour, for each day, the waves were classified as yes, no, or maybe. And so in order to be considered yes, the waves must be present throughout the entire box for the entire hour. And then they were considered a maybe if there were waves, but maybe not for the entire region or for the entire hour. And so now I want to sort of present the distribution of snowfall rates when we had velocity waves and when we didn't have velocity waves. And so this figure here shows the wave existence on the x-axis and the precipitation rate on the y. And the points are jittered just so that you can kind of see the separation. And really kind of the takeaway here is that we really didn't see waves all that often. Only about 191 hours out of our entire over 4,000 hours did we actually see waves. However, when we did see waves, there was a slightly higher median precipitation rate. And so I just have a slightly different way of looking at this, combining from the two different regions. These are just two histograms where the left-hand side is when we did have waves and the right-hand side is when we didn't have waves, and just highlighting those median precipitation rates. We wanted to check to see if these medians were statistically kind of significant. So what we did was we randomly sampled 191 points from the entire data set of precipitation rates. And we did this 10,000 times and calculated the median and mean, which is what's shown in these histograms here. And then we compared the 95th percentile of the random subset of the medians and means to the median and mean from the time that we did have waves. So in this case, it's sort of just trying to get at if the subset of times with waves could have been randomly sampled just from the general entire set of times. And ultimately what we found is that the median and means were both higher than the 95th percentile, which actually indicates that the times with waves are not likely to be random. It actually is greater. The median and mean is greater than times without waves. We also wanted to look at the distribution of locally enhanced features from times with waves to times without waves. And so these are just the feature area times time fraction 2D distributions. But ultimately here, there were just really too few observations to infer any associations between velocity waves and snow bands. So now to summarize, what we really found with velocity waves is that they're generally very uncommon for a given geographic region. When they do occur, we do see a slightly higher median, but ultimately we're not really sure why this is occurring, and it really needs further study in terms of if velocity waves are associated with large-scale conditions for precipitation, or if the velocity waves themselves actually kind of enhance the precipitation. So this is kind of still a open-ended question, really. So again, I'm just going to kind of go through my previous summaries just in terms of what we found in terms of storm structure and evolution, where we found the high precipitation rates relative to the low pressure center, and when we found them when the surface pressure was decreasing. The summary from the enhanced reflectivity features, where most of the time the snow rates are low and there doesn't seem to be an association between the locally enhanced features and the snow rates. And also just kind of the really interesting and high resolution vertical cross section showing the lack of vertical column continuity and how these features just end up getting tilted and smeared as they kind of get transported by the wind. So now I kind of wanted to step back and talk about how my findings fit into the context of previous work. So I kind of brought this figure back from earlier in the presentation where I was talking about primary bands and multi-bands. So primary bands were, a lot of the work, like I mentioned, was primarily case studies. Essentially, there would be these kind of crazy, really high impact events of heavy snow. And then we would go look at kind of what's going on and kind of just look at these individual cases. And they did find that the primary bands are associated with strong frontogenesis, where we're kind of seeing favorable locations for precipitation growth. But another study looking at kind of a larger data set from Ganetis et al. Found that primary bands don't really occur all that often. She also found in her work that multi-bands kind of form in all kinds of environments, and they form much more frequently than primary bands. And so in terms of my work, what we find is that for all types of snow bands, they are not typically associated with high surface snow rates. So that's sort of kind of how my findings here fit into kind of what we learned from previous work. So now going into a little bit of the implications in terms of snow in low wind, non-blizzard conditions. Heavy snow rates in Northeast US winter storms are rare. 75% of hours had light snow rates and only 6% had heavy snow rates. In general, snow bands are a distraction when it comes to forecasting heavy snow because they are rarely associated with heavy snow. Even when we have a lot of features surrounding the area, less than 1 out of 4 hours are associated with heavy snow. Ultimately, locations with long durations of snowfall are more informative when it comes to forecasting high snowfall accumulation. So in terms of what to focus on, kind of just have that summarized here. Times and locations where the low pressure is deepening, locations for large scale lifting. We kind of already knew this from previous work, but ultimately this work shows that rather than focusing on snow bands, looking at the duration of all snow precipitation radar echo. Okay, so I made it to the end. I have a lot of people to thank. First of all, I'd like to thank my advisor, Dr. Sandra Yuter. I just really appreciate all the guidance and support over the past over 10 years. Also like to thank my committee, Dr. Parker, Dr. Marilla Tolbier, and Dr. Baker Perry. Also, I have to thank Center for Geospatial Analytics just for financial support, but also just for creating such a great environment to do this program. It's been wonderful. I have to thank the Environment Analytics Research Group, Dr. Matt Miller. He's not here today, but he was just a great help in just helping with this project and just all of my technology problems. The graduate students, particularly Luke Allen, just great help in terms of data and just bouncing ideas off each other. Kevin Burris, Rachel Kennedy, Laura Kent. Undergrads, some of which are here, they were really invaluable in terms of helping process a lot of this data, classify the waves. Jordan Fritz, Anja, Mackenzie, Cameron Declan, Robert Harley. And then I'd also like to thank two previous grad students, Nicole Corbin, Nicole Hoban, NASA Impact Science team for the data for the project, Stony Brook collaborators, Dr. David Novak at the Weather Prediction Center was really great at providing feedback for this project, NSF and NASA for funding, and then of course my friends and family. So with that, I'll take any questions.
All right, so I guess maybe we'll start with questions in the room.
Sure.
You might have mentioned this at the beginning, but I guess conceptually, will you remind me why you were most interested in non-blizzard conditions, like what the challenges of non-blizzard conditions were versus blizzard?
Yeah, so I don't know if people on Zoom could hear that, but someone asked about why I looked at non-blizzard conditions versus blizzard conditions. Ultimately, this really came out of the fact that in terms of measuring precipitation at precipitation gauges, snow, it's really challenging to measure snow in really high wind conditions. So a lot of the time the gauges will underestimate how much snow is falling. Also, I think in general, blizzards kind of tend to be at the real high end, like the extreme end of things. So I was sort of focusing on just a very kind of general subset of the storms. But yeah. Yeah.
Got, I guess, two questions online.
Oh, yeah, I can pull it up. Okay, so Gail Script asked, is it fair to say that radar is far more effective in predicting rainfall than snowfall? I suppose I would say yes. I think, but I don't really, I don't know. I haven't actually really looked at that. But I think just in terms of how the radar observations of rain, they kind of fall a little more straight down, less kind of transported by the wind. So I would say yes, but I also know that radar, it's very tricky in terms of predicting radar. So yes, but with a caveat, I suppose. And then Bryce asked, is it possible that using liquid water equivalent removes the possibility of detecting regimes or processes that lead to high snow rates because of high SLRs? Snow liquid, I can't remember what SLR, but essentially the ratio between snow and liquid. That's, I mean, I think yes, it does. That sort of ends up, that was sort of why we use liquid water equivalent to remove the uncertainty with SLRs. Ultimately, we chose to use liquid, well, that's why we chose to use the liquid water equivalent, but I think that also ends up relating more to just the impacts of precipitation and kind of the watershed implications. I just really didn't want to mess with SLRs. There's so much uncertainty. But yeah, I mean, I think it's possible that it does kind of like limit some of that interpretation. Okay, and then Chip has his hand up.
Yeah, I always got to ask a question. So first off, great talk. Very interesting stuff. So in the wave analysis and also in the algorithm-based banding detection, what elevation were you looking at? Was that just like the base elevation, or was that a constant altitude, or what sort of level was that?
So I was looking at the 0.5 degree elevation angle, and so that changes based on the relative location to the radar. But I ultimately chose to use that because I didn't want to interpolate to a constant altitude and kind of remove some of the high scale detail in some of the observations. So that was sort of my big caveat with with the radar observations is that they aren't at a constant altitude.
Yeah. So did you happen to look at any of the other elevations, especially with like the wave analysis, like where the waves did the waves tend to always be like restricted to like only a like low elevations, or when there were waves were they at, you know, up at higher elevations as well?
No, I didn't look at that, but
Okay.
I believe one of the previous student that worked on this did look a little bit more in detail about that. But yeah, I think waves can kind of be found at all elevations.
Yeah. It might also be interesting to look at multiple elevations with the banding detection, just to see if you can't, you know, match up the change in the band location with the wind profile. But yeah, thanks for the talk and great work.
Yeah, thank you. Okay, so Daniel asked, could you talk more about the threshold sensitivity analysis for the area times time fraction metric? You mentioned this briefly, but would love to hear more about this since it's so central to the analysis. Yeah, so okay. So the first thing I looked at was because we kind of chose a 25-kilometer radius surrounding the ASOS station, I wanted to just test to see if changing the radius would change the results, since there is kind of a lot of variability. And so ultimately, like, that didn't really change it. One of the things we also looked at was the lag between the observations. So originally I was pairing the observations directly for the same hour. Then I also wanted to look at, okay, if there are features in this hour, does it change the precipitation rate for the next hour? Since there is some, because of the vertical changes, like there is some possibility that snow falls very slowly. And so we wanted to kind of test that as well. And then I also looked at the influence of the beam height, because again, snow falls slowly. And so for some stations, perhaps the reflectivity features at a certain altitude might kind of impact when it reaches the surface. Ian asked, is the reason that the Boston forecast this past storm was so bad because they were relying on where the snow bands were? So actually, not necessarily. I think the kind of the issue with this forecast was partially related to where the low pressure center was, and also related to kind of the general how far away from the low the precipitation was going to extend. Is there an indication moving forward based on your findings that forecast should only take into account the modeled duration of overall precip? So, I mean, I think my work is kind of a little more related to, we call it nowcasting, which is where we kind of forecast almost in real time. And I think my results are kind of more applicable to that and less applicable to modeling. Modeling is like pretty complicated, and I'm not necessarily sure that where my results fit in terms of modeling. I think maybe we could say something about that. But ultimately, I was kind of looking at this in terms of nowcasting and looking at, okay, here's radar observations. Where are we going to see heavy snow? Yeah. Okay. Yeah.
Yeah, I was curious, are there impacts from like long-term climate or like El Nino oscillations on the physics or characteristics of these storms that impact their forecastability?
Yeah, I think so, but I haven't really looked into that. I mean, I think El Nino and La Nina kind of influence like really large scale patterns. So I think they influence kind of like the locations of the low pressure tracks themselves, but I'm not really sure that they kind of influence some of these smaller scale features.